So we will speak about the next of the story. So thanks for one time for Christian to find it, because after it was a great story. So we start the beginning of the story. So the asteroid part, the fireballs part, and also the Stonefield part. And after, Brigitte will speak about the recovery campaign and about the study of the meteorite. Okay, so first, in fact, just a few words about FRIPON and Vigie-Ciel. So FRIPON is the network for international network. Now we have 200 cameras working. And Vigie-Ciel, in fact, is a science citizen program in France. So it's helped us to search the meteorite. And you will see after. Okay, so just a map of the FRIPON network. So you will also talk about, for example, the new Chilean camera. And so it's made in Europe, okay. Okay, and Vigie-Ciel, in fact, is a science citizen program. Most of the people who help us belong to the Vigie-Ciel network. And also to local people in Normandy who help us. And it was very efficient because there are many other researchers who find the meteorite and keep the meteorite for them. Okay. So here is the Vigie-Ciel network. Okay. So I will be fast for this part because you you know all about Christian discovery. And for me, it was a pity because, in fact, this weekend, I was ill and I go to bed at 10, which is completely unusual for me. And I missed totally the event. And the worst thing is that from my window in Paris, it was possible to see the event. So it was just very, very, very bad things. Okay. So this is, you see also these things. Okay. So in fact, what things is very important, and we will, is that this event was observed by many people, so by amateurs, by professionals, and at any level of the search, of the discovery. In fact, it was a mix between amateur and professional, and this is very important for us. And without that, in fact, we were not so successful. Okay. So Carl Lantier write very quickly news about that. And so also in the EMO website, there was a news. Okay. And so many people observe it. So Jocelyn Demar was a colleague at the Paris Observatory, and he go outside Paris to observe it. And this video image was very important for the next of the story to have very accurate position. Okay. So this is from UK. Wow. Okay. And so it was observed by also many other things, like seismic detector and also sonic waves. Okay. And you see, in fact, and the first, in fact, location of the impact was in the sea. So people say, oh, it's all in the sea. So it's and after we have another prediction to see it. So this is the observation made by FRIPON. And by FRIPON, in fact, we are unlucky because this night it was very cold. It's like about 0 and also very humid. So we had a lot of dew on the dome. And in fact, we have problem of detection, and some of our cameras were completely wet. And in fact, the detection software doesn't work well. And so we have just a few data with FRIPON. So it was really also a pity about that. But we have good data for, you see this. This is from Rennes. And Rennes, in fact, it was on the top of the planetarium, very high level. And so we have no dew like in the other camera. Okay. And so, in fact, to solve, in fact, this the problem, in fact, we have to put many things together. So the optical data, the seismologic infrasound to get trajectory, it's very important also to have several manner to measure the initial mass, for example, and with the trajectory, with the energy, and also with everything. Okay. And also to have an idea of fragmentation, to have a good idea, a good estimation of the dark flight. You will see the dark flight is really a complex things. Before this event, I think that I thought that dark flight was easy to compute, but in fact, it's not so easy. You have to to make many things. So, for example, it was very important to have this very fragmentation. You see the fragmentation. So it was important to have this video, which was very sensitive, more sensitive than FRIPON, to get the information on the fragmentation, because fragmentation is very important for dark flight. Because in fact, if you see a fragmentation, you know the altitude of the fragmentation, you know that there is some rocks that are produced at this altitude, and they have not the same trajectory than the main mass, for example. Okay. So this is a computation made by mainly by Denis Vida and the Canadian team. And it was important to see that for the first time, in fact, we can connect the orbit, which was calculated with telescope, so from the asteroid part, and also with the fireball part. And because it's the first time we have all this data together, and to have a good observation of the fireball event and also the asteroid part. And we see that, in fact, at the end, we have a very good connection of the trajectory with an accuracy of 200 meters. Because it's not easy, in fact, when you have the fireball to come in the past and to have a real idea of the orbit. Okay, so in fact, it's a basical meteorite with a source in the main belt, and so with the classical resonance, like Nucis, from most of the INEO. Okay. And you see that the dark flight, how it works. So you see there's the several mass. Of course, the big mass are on the right, and the smaller are close to the sea. So we are really happy to have this fall on the land. Okay. And so we start with the story about the dark flight. So there are many people who compute the dark flight. So this on this part, it was calculated by Denis Vida. This one was by the guy of Strunity Field, and also the Czech people compute this one. And you see that, of course, it's close. When you see the scale, it's kilometers. So when you are on the ground, it's not so easy to say, we have to find this thing. So and it is important to have some idea where to search in first. And we are lucky to have Peter Geniskens who come with us, and we give us a good idea to search, because if you have only this, it's not easy to say, we have to start by this point, because it's like 10 kilometers from one side to another one. And okay. So this is still the computation of the dark flight. Okay. And at the end, we found a big piece, 100 kilograms piece, but it was not on the good location. It was normally it was a location of a small piece, because the idea of Peter was we have to go to search for small piece, because there are many small pieces and they are easier to find that only the big piece, because the big piece can fall in a complex location, and it's more easy to find small pieces. But in fact, we found a big one. So we have to change the computation of the storm field. Okay, so the basic part of the storm field, we have the start, or also the fragmentation. And if you have fragmentation, you have different location for the fall at the end. Okay. And so where is the problem? In fact, you have the main flare ejection, we see. So when you have the fragmentation, we produce this strong field. Okay. And we have the other strong field made by the end of the fireball. And you see that at the end, for the big mass, it is on the same location. But you have, you see, on the star as a location where we recover the meteorites. Okay. And maybe you want to continue?
Okay. Okay. After the first initial discovery, one thing that's important to say is the press got involved very early on, and for the first couple of days, we had 2 people of our team who just answered questions from the press, from the media. We're just totally occupied with that. It's just a small sample of the requests we got, and we're very, very, very proud with this issue. Then we continued the search for during on and off for 2 to 3 weeks, and we got some of the lucky people that were involved, some people of the Vigie-Ciel team, and that includes children coming along with their parents, and some of them got lucky. But after a while, they were not just our teams, because we are very careful to ask the owners of the field whether we can go in and search. But there were independent hunters who came along, and there was lots of them, and they started going everywhere, and not all of them were that careful, asking for permissions to go in the field. So labels like that started appearing on the doors, because people really got very tired. And also among the independent people, we had people coming from different countries, including a team of well-known American hunters. And they were very lucky. Within 2 days, they discovered a bigger sample than the one we had. And they're on the beach.
USA. We are in Normandy, France, on the beach.
Where the greatest generation laid down their lives, the beaches of Normandy. It did get. It's still wet because we washed it off, which is really the worst thing that they can do. So that really, in France, there is no law at present, and on the ownership of meteorites, there's only jurisprudences, and depending on whether the meteorite landed on the ground or whether it's in the ground 20 centimeters further after millions of kilometers, then the jurisprudence is different. If it's on top of the ground, then the finder keeps it. If it's 20 centimeters in, then the owner of the land has gotten to keep it, which is totally, obviously, stupid, because it's just the same object. So for years, we've been asking to get a law organized, but we had a request from a representative to the Minister of Research 5 years ago. Then there was we were told, no, it has to be done internationally. And then there was COVID, it all fell down. And last September, we had restarted that. And we got the same answer. And we were in the process of replying to the minister when that fell. And so I downloaded this video, which was 6 minutes. I shortened it a little bit because it wasn't fascinating, to be honest. But the people at the ministry, they were in total shock when they discovered that. They said, you're fighting against private hunters? I said, yeah, there's no law. There's no law. There's nothing we can do about keeping meteorites like that. And they are precious objects for research. They're saying that they saved France because what happens is when a meteorite is in the ground, it's exposed to alteration by water, terrestrial water, basically, and it will rust very fast. We'll see that very soon. So it's important, contrary at the difference with archaeological objects, it's important to retrieve it as fast as possible from the ground. The result of the field searches, all the rocks that we found, except number 1, which was the first one, 94 grams. But we think there are at least 50, probably more fragments that were found in total by the private hunters. And we think there's 1 to 2 kilos. We don't know exactly. So once we got the rocks in hand, we look at them very carefully. We describe them. For example, you can see on the one on the left, which is the one that Peter found, you can see that there are 2 levels of crust. Oui, mais j'arrive pas à l'allumer. Ah, c'est ça. You can see that there are two different types of crust. This is very smooth, and this is a lot more corrugated. And I think that means this corresponds to two different breakup. This was higher up in the atmosphere, and it was lower. So we can look at samples and have some idea of the fragmentation. This is one of the first rocks we found, and that is the first one we sampled, and it was found about a week after the fall. But this was found 2 weeks after the fall on a tennis court, and because it was on the tennis court, the water was running away, and the result was that this one is much more rusty than that one. So within a week, this got really, really rusty. This was protected by water, it didn't. So that shows that it's really, really urgent to remove the stones from the ground. So once I have the first stone in the museum, I saw it, looked at it in a different, that's just a sawn part where you can see shock veins, metal grains, that is different rock units. So it's what we call a breccia. That's a rock that's the aggregation of previous rocks. This is electronic microscope, and that allowed me to classify the meteorite, and then it gets published in the Meteorological Bulletin of the Meteorological Society. And what did we say? It was an L56 breccia, and its shock type is 3. So what does that mean? Very, very briefly, this is the story of accretion and differentiation of asteroids in the, after they were formed. I don't want to go into any detail like that, but this is the story of large bodies like the Earth, planets, which get differentiated. But most meteorites that we have, they come from bodies that had an evolution that aborted. So they were heated in the protoplanetary disk, but they didn't melt. And most bodies that we get got heated that way, and they stopped there. This is chondrites that we have. And how do we see that? This is what we call a thin section. It's a 30 micron thick slab that you look at like a stained glass window. You look at it in a microscope, and this is what you see in reflected light. And without going into any further explanation, we can talk about it later if you like, but you can see the chondritic texture, the little beads there that disappear with heating. So we classify samples between type 3 and type 4 for the transparent mineral, the silicates, and for the opaque minerals here, which appear in white and pinkish. And you can see the shapes change. And based on those observations, we can tell how much a body has been heated. And what is here is a classification. I'm sorry, it's in French. Different types of chondrites are represented here. Ordinary chondrites are the most common. And what you can see here is different bodies, but what you have here is different levels of heating. And each type, 3, 4, 5, 6, correspond to a rough temperature that we have more or less estimated. So Saint-Pierre-le-Viger is a breccia, 5-6 breccia. So that means on its parent body, when it cooled down, initially, it was heated between 700 Celsius and 950 Celsius. And also it's among the most common objects that we observe to fall. We can reconstruct the story of such objects. We can tell, for example, depending on how fast the bodies were accreted, and that depends on how far from the sun it accreted. You expect different structures for the different parent bodies. And we think chondrites accreted very fast. So there is a lot of type 6 material, which appears in red, and very little type 3 material, which is the material that was on the surface that cooled very fast. Whereas if we had slow accretion, we'd have a structure that is more like that. So we think chondrites accreted very fast and got mostly heated. And we can reconstruct their story. What you have here is a time diagram, a time sequence. This is 2 isotopes of lead compared to 1 isotope of uranium and 1 isotope of lead. And this curve here, it goes in time. And what you expect, if your body had that type of structure, then you expect the outside layers to cool down faster than the inside layers. And this is exactly what you see for H chondrites. You have the outside layer was cooled down by 4.57 billion years, whereas the inside layer cooled down more slowly and cooled down only by 4.5 million years. But in L and LL chondrites, it's much more confusing. The things are not in the right order. You've got type 6s here, type 6s here, type 5 here. Everything is mixed up. So we think these bodies, they broke up very, very early on in the process before they were totally cooled down. So we think there was a catastrophic collision very, very early on before the bodies were cooled down. And then there was reaccretion so that they could finish their cooling down in a massive body. And then when we try to further reconstruct the story of different asteroids, we look at the gas retention ages of the different bodies. And for L chondrites, which Saint-Pierre-le-Viger is an L chondrite, what that age is the last time that the body was heated above a certain temperature, above which all the argon is lost, basically. So what you monitor is the last time it was heated above a certain temperature. Most L chondrites, they were heated above that temperature, which is something like 400, 500, 600 Celsius at 470 million years ago. So we think there was a major disruption of the L chondrite parent body 4.7 million years ago. And of course, what we have to check now is whether Saint-Pierre-le-Viger belonged to that series of rocks which were broken 470 million years ago. So that's one of the things that we are going to measure, the gas retention age for Saint-Pierre-le-Viger. Of course, I don't want to get into the detail, but we have only the end of the story. There might have been several episodes before. We would not see them because the last one erased everything that happened before. Now, the next question is, was that the event that produced the 2023 CX1 asteroid? In fact, this is too short a story. The last steps of the 2023 CX1 saga are recorded by cosmogenic nuclides within the meteorite. What happens is when the body is exposed in space to galactic cosmic rays, they will induce spallation reactions, and those spallation, they break up big nuclei and they make smaller nuclei, so that's nuclear reaction. And that happens roughly between the first meters of the small bodies. And what will that do? That will produce different new nuclei, stable isotopes, and these will just accumulate with time. So they will give us an idea of the duration of the event. But also there are short-lived radionuclides, and these at some point, they will start decreasing at the same stage as the time they're produced. So you get a secular equilibrium for these nuclei. So that means that these nuclei, the abundance of these nuclei is totally independent of the time during which the object was irradiated. And that will be useful in terms of reconstructing the condition of the irradiation. Because in fact, there are three unknowns. The duration of the irradiation, so the stable isotopes will tell us that. The size of the asteroid, which we will have some idea of with short-lived nuclei or radionuclides, and the depth of irradiation, because obviously the cosmic rays don't penetrate all that far. So we can use also some of the short-lived radionuclides and also some ratios of stable isotopes to deduce that. So we build up that kind of model where we look at the concentration of those short-lived radionuclides as a function of depth. And for different radii, these are model calculation, and then you can compare it with the abundances of these elements which are measured in the bodies. So that gives us an idea of so these two nuclei, this is for the Park Forest meteorite. For these two nuclei, you can have a good idea that the ratio of the initial body was somewhere between 40 and 50 centimeters, but then you can see it's rather flat, so you cannot deduce the depth of irradiation just from that. So you have to use other elements. So for the case of the Park Forest meteorite, they use the ratio of neon 22 to neon 21 to get the depth of irradiation. So we are obviously going to try to do the same story for our meteorite. These are the different nuclei that can be measured by different techniques. Once we have that, we can get an idea of the exposure age. I want to get into this. This is really important. The age, the duration of exposition, which we call the exposure age for chondrites, they are mostly between 10 and 60 million years. There is nothing that is 470 million years. In fact, there are no stones that are this irradiation age. They're all roughly 100 million years at most. And why is that? I think it's because these objects do not survive longer than that in space. There are iron meteorites which are older, but there is no stones which is older. So what does that mean? That means that presumably, I mean, we'll measure that age for Saint-Pierre-le-Viger, but presumably it's also less than 60 million years like the other chondrites. So that means that the story is more complicated. After this event of breakup 470 million years ago, there must have been either a large residual fragment or there must have been some kind of reaccretion, so that there was a late impact that produced the 1 meter body. That was the one that eventually arrived and that Christian observed that fell last February. What are we doing? Well, I told you we have about 12 samples that we have sampled from. And what we're doing is we're trying to measure all those short-lived radioactive elements and all those rare gases in samples that come from different areas from the rock, hoping that they come from different depths inside the initial body and that we can actually reconstruct its fragmentation. Of course, we'll compare that to the observations of the rocks themselves. We can compare that to the visual observation of the fragmentation that François talked about. And we also have some information from the seismic and acoustic data. And we hope that with all this info, we can actually reconstruct how the body really fragmented inside the So that's a summary of the ongoing analysis, petrography, bulk chemistry, oxygen isotopes. All of that is more or less done. Noble gases, I think they're done already. We don't have actually the results. They need to be treated, but they will lead to all these results that I talked about. So that should allow us to reconstruct the story of the parent body, the collision, and the fragmentation history. One last point. What about the American stone? Well, this British collector decided that the main mass of a rock could not be destroyed, should not be sampled, should not be cut. And he bought it from the people who had actually mailed it to the US immediately. And then he delivered it. Actually, I went to get it in London, but it's deposited at the museum. And that's the inauguration of the showcase with that rock and the other rocks with the president of the museum. And we were lucky that we'd spent a lot of time in the field. We'd been back to give conferences there. So at the inauguration, we had the owner of the land on which that meteorite was found. That's the mayor of the next town. That's the president of the commune and it was an elected person as well. So everybody was there. Also the young woman who found the first meteorite. This is my last slide. What I want to really stress is that at every stage of this work, we have both professional networks and amateur people who are involved, observers which are involved at every stage of the point. Christian, I wasn't sure where to place you, but whether you were in it doesn't matter, but I wasn't sure whether it should be considered a professional body or not, but it's not important. You tell me later. Anyway, what I wanted to stress is amateurs were involved at every stage of the way. Also observing the meteor, and in particular, Oriane, who is leading the whole group. They got in touch with many amateurs who had deposited their observation on the IMO website. And these people, a lot of them went back to where they shot their pictures so that they shot new pictures of the sky in the same conditions so that their cameras could be really properly calibrated. And that was very useful in terms of reconstructing the trajectory. Of course, at this stage, there are professional and amateurs looking in the field, and all of this contributes to a scientific study that will be really largely international. There are more than 10 countries that are involved. It's really interdisciplinary. I think it's really important that we have people involved from a professional astronomer who look in space, people who look at meteors in the atmosphere, people who study meteorite, look at the field and study meteorites. So it's really, really interdisciplinary, and it's a pro-am study. Thank you.
Thank you, François and Brigitte. This is really amazing. And indeed, as you said, it's throughout the whole different communities. It's a success story. Are there any questions from the public? Do you have a question on this talk, Hervé, or no? Microphone to it. Okay.
Yeah, so in fact, this is a question both to Christian and François. I think this was really exciting to have an asteroid which becomes a fireball, and then we find a meteorite, and we see it even coming. How often can we expect such a thing in the future? Is this a unique event, or will it happen more frequently? There's all the modern camera systems and analysis tools we have.
I think finding an impactor would be more fun now, but the event will fall in a country like Europe, so it will be not so often. I think so, and I don't know, because it's a small event, fast small number event, so it's difficult to make statistics. But I think the same thing in Europe is for I don't know, 1 century. It's almost like that, I think. Maybe I'm wrong, but
Okay, thanks.
no, question?
In my opinion, the larger, the EB5 type 5-meter objects hit the Earth 1 or 2 times per year, the war Earth. The CX1 maybe weeks. It's a not very event, but the oceans, the Sahara,
Yes.
we have some problem, observing problems.
Just to comment, I guess with LSST, we will see more and more of those. So, and we see several falls per year over France. Now, to recover them is still a big challenge, but I expect more of them to come.
I think it's what they said, but I'm not sure.
I also want to stress that everybody was very well coordinated for all the observations that came afterwards. ESA reacted the Minor Planet Center reacted very fast. ESA reacted very fast. We reacted fast. I think this will happen more and more, that we'll have more observations along all the line, because people are more aware. And I think even there is some talking of trying to catch the spectrum. At this time, it was too difficult, because you'd have to take one telescope off of what it's doing and derouting it to doing something else. But I think this will happen more and more. We will be more and more ready.
We were on the field like 30 hours after the fall. It was very important to find.
Yeah, well, first of all, compliments for this fantastic story. It's really fascinating. I have one particular question for François. In the beginning, you showed us a sort of a map with these different strewn field predictions.
Yes.
So which one was closest to the actual fall locations? And could you explain what could be the potential difference between these different models that are being used? Because I'm curious to see these.
In fact, it was funny, because during the story, we found the meteorite, we found the location. After we sent the location to the Canadian team, to Oriane and Denise, and they compute at each day a new strewn field. And in fact, you have many unknown parameters to compute the strewn field. So in fact, it's like cooking something. You have to. At the beginning, I think it was more easy than that, but in fact, it's a really complex thing to compute this strewn field.
It was also the first calculation within 2 days. I mean, things got refined with time. And we didn't have properly calibrated images or anything. Everybody had partial information. And as the information got refined and more precise, then the strewn fields got better and converged.
And for example, there's an important parameter is the shape of the object, the shape parameter. So it's a sphere or it's a square or anything, and it changed many things. And so at the end, you say maybe it's this, but it's just that the computation fit in fact the data of the force. For sure, it's not well.
Thank you. I have a question that there was a slide with the fragmentation from the smallest one to the 490 grams.
That one?
Yeah. No, at the end, maybe. And what do you think? Maybe is there a field with a bigger particle?
For sure, the bigger particle are on the right.
Yeah,
on the right,
yeah.
on the-
No, maybe the last slide or.
Ah, oui, oui. Ah, on n'a pas le.
Yes, normally it's 2 kilograms.
Yeah, yeah.
Again.
So which is the
Normally, we're still
this
Ah,
slide? So
oh,
there is
that 400-gram piece was found.
yeah. So maybe
on his tennis court.
there is maybe there is the biggest.
yes.
Yeah,
Yeah,
there
Is
could
there any chance
there
for-
could easily be.
It's still here, but in fact, must be buried like. We have to go back for sure. The problem is that at that time, just before, in fact, there are some station for now we can go back to work. But it will not be easy. It will be not so easy because in fact the farmer have
Oh, there.
their field, so but it's a big piece. So
Nice work, guys. It's a very exciting story and an exciting meteorite. I was only aware of this 175-gram piece that Steve had found, but the rest of these finds, how did they line up with the original IMO stream field that Vigie and Pavel made?
I have to go back there. They were all displayed on it.
Yes.
They're all displayed.
you have the stars.
All the stars are where the rocks are.
Yes, yeah.
The first rock was found there, and that corresponds to the main line. And you move along this line just by changing the shape of the meteoroid when you do the calculation. So obviously, by replacing
Right, no,
like
I
the
understand
bricks.
that. I'm saying, where does the original IMO stream field that we published the day after this fall
Oh,
with
the
regard to all
original
those stars?
strewn field. I think it's.
Just a tad south.
I think it's somewhere over there. No? It's out. Okay.
It's more.
Okay.
Yes, yes. And what we did.
Yeah, this one. I'm just curious. Where real fine.
So you can see the little
Ah.
town that's in Pavel's
This
strewn
did
field
not
there.
move. This did not move. What moved is the mass of the samples, but this main curve did not move, in fact. What moved is along the central line, the mass of the samples were shifted, but the actual, so the heavier samples were there. Instead of being 10 grams, we're now 100 grams here, but that line, the line itself did not move. And then there's the second flare ejecta, which is somewhere there. And in fact, it's in the
It's
the
on
Merclot
the
coast-
top, the yellow line that's at the
Yeah,
top
right.
of
Huh?
the distribution.
Yes, on the
Yeah.
check.
Yeah,
so
yeah.
The
Okay.
small piece were.
Ouais, Angien, c'est là. Hein?
So
Ça,
it's
c'est
basically
Angien.
on that
They're
top
over there.
line. So they were very close. Yeah. But the difficulty at the very first day was there was just a lot of confusion.
Mm.
We didn't quite know how high the breakup point was.
Yes.
And that determines where your strewn field is. So you get this whole range of strewn fields. And so if you have that uncertainty, what you do is you follow vertical tracks through the field. So initially we followed vertical tracks through the field that sort of came from the endpoint. And we ended up with the first find. And then that turned out to be much bigger than what we expected it to be. So the breakup was definitely higher up. And so then when we did vertical scans 4 points higher up, we basically found the second meteorite with 3 grammar, and that was at the top yellow line where both Vigie and Perch have their curve. So you see, yeah.
That's
A little bit above,
yes.
yeah. And once we found that second one, hooray, now we had the whole strewn field mapped.
Thanks. This is regarding the explanation you gave about how the composition was formed, that you cannot explain with just one collision. When you explain about the composition, how the particle was formed, that you cannot explain with just one collision, and you put like a picture of like 2 collisions or 2 consecutive events. Will it be possible to explain it with predeposition of the material a long time, like we have seen in other objects with time? Or
I only half hear you, so I'm not sure I understand your question, but we analyze a lot of isotopes and a lot of rare gases, and because all of them, the production reaction are not that well known, it's not that precise, so we try to match all these info. But what I think we will have is we have 5 samples, unless I'm mistaken, for which all these elements will be measured, so we can tell at which depth they were irradiated. And of course, the size, the initial size of the body, we don't need to calculate, really, we know it, it's been seen. So all of that should allow us for each sample to tell us exactly which depth it was from. How much further we can reconstruct the event of fragmentation, that remains to be seen. It's a difficult task. We are trying to do it, but I don't know how well we will succeed. It's the first time it's done, so.
okay,
Does that answer your question?
more or less,
Okay.
but okay, thank you.
Thanks.